Hello all, welcome to week 9. In this week we'll be discussing about the failure of the laminas as well as the micromechanics. In this video as well as the next video we'll focus on the lamina failure. Uh, if you recall, in the last video we introduced to you the fundamental strengths of the lamina. We showed 5 fundamental strengths. So we'll build up on it and see how we can define few failure criteria which are specific to composites. So this will be the outline of this video, where we'll first briefly review the fundamental strengths in lamina that we already discussed in the previous video. And then we will move into biaxial loadings. So since we already know that in real world the loadings are multi-axial, meaning they are not, it's rarely that you get a uniaxial loading. Most often they are like loadings in 2 or 3 directions. So how do we know or predict that in under certain multi-axial loading conditions whether a composite is safe or not? For that we have to look at failure criteria where we can apply for multi-axial loadings. So we'll start with isotropic materials because we'll build upon it to develop the failure criteria for the orthotropic materials. Though there are several failure criteria available in literature for composites, for our course we'll focus on 4 commonly used failure criteria, which are the maximum stress and maximum strain, which are mostly for academic purposes and which are rarely used. But Sahil and Hoffman are the ones which are mostly used in the industry, so we will also focus on them. So let's start to look at the fundamental strengths of lamina. Since we have already looked at it, we'll pass through quickly. So we said to define the stiffness of the lamina, we use the material properties E1, E2, Poisson ratio nu12 and shear modulus G1. But if you are looking at the strengths, we start with Xt where we define it as the longitudinal strength in tension. Corresponding to this strength, we also have a failure strain which will define it as x of epsilon t, which is again given in terms of x of t, which is x of t by modulus E1. So this is the longitudinal strength and the corresponding strain also we have shown here. Similarly, we'll also have longitudinal strength in compression. So the difference is previously it was in tension, now it is in compression. So we show it with a subscript C. So for the strength, we have a corresponding failure strain given as epsilon C, where again it can be written in terms of strength by modulus E1. So these two are the strengths in the longitudinal direction, which means along the fiber. Now we look at strengths perpendicular to the fiber, which are given by these YT, transverse strength in tension. The corresponding strain, we will write it as Y epsilon T, which is again given in terms of strength YT divided by E2. Since we are now loading in the direction 2, so we will use the modulus E2. And then we also have another transverse strength in compression this time, and the corresponding strain we'll write it as y epsilon c, which is yc by E2. And lastly we have for shear strength S, and the corresponding failure strain we'll write it as S epsilon, which is again given as S by G1. So here we have shown 5 fundamental strengths if we are focusing on a planar or let's say plane stress situations. And in addition to these uh, 5 strengths, we also show 5 corresponding failure strengths. So we'll use this to define the failure criteria which we need to predict whether a composite fails or not when the loading is multi-axial. Okay. But in addition to these strengths, we also need to discuss about the failure mechanisms in the composite. So let's say in each of these failure strengths, let's see if we can identify any failure mechanism. So let's start with the longitudinal strength, which means we have a composite where the fibers are along, the loading is along the fiber direction. So the kind of failure we expect is the fibers to fracture. When we talk about compression and we are loading in the direction of the fibers, then one failure criteria is the fiber buckling. And when we are now loading it perpendicular to the direction of the fibers, the transfer strength in tension, here it depends mostly on the matrix fracture or failure. And even in compression, we'll see that matrix is the one which usually fails. So we'll again write it as matrix fracture or failure. And lastly, related to shear strength, it can be either matrix or fiber. So as we can see, these are the some of the failure mechanisms which are commonly found, and these failure mechanism will depend on what is the nature of loading, whether it is tensile or compressive, as well as whether the loading is along the fibers or perpendicular to the fibers. What we have shown here is only a few of the failure mechanisms. There are many more mechanisms, because we can also talk about failures happening at the interface between the fiber and the matrix, as well as we can also, if we now move from lamina to the laminate, then we can also talk about failures occurring between two lamina, where two laminas are joined together or glued together. Okay, the reason why we are discussing about these failure mechanisms is we will see if we can relate these failure mechanisms with the failure criteria or not. Okay, so now we move to biaxial strength. So we already mentioned that in real world or the real world composite structures, it is expected to see multi-axial loads. So we need to be able to predict whether this particular lamina fails or not. So how do we consider these biaxial strengths is what we are looking at. So let's start with isotropic materials, where we have already studied in our previous courses when we were discussing about metals like aluminum and steel, so which we call it as isotropic materials. Let's say this multi-axial loading can be represented with a infinitesimal element. Let's say this is the infinitesimal element where we have loading along the x-axis sigma x, along the y-axis sigma y, and then there is also shear loading tau x. So when we have a biaxial loading like this is the plane stress, let's say, or 2D stress state. Hmm. So when we were discussing about isotropic materials, the way to look at this with regards to failure is we will try to find out the principal stresses sigma 1 and sigma 2. What are principal stresses? These are the stresses on the planes where there is no shear. So let's represent that principal stresses. So what we mention is, let's say this is the infinitesimal stress about this point O. About that same point O, if we now change the orientation, meaning for the same point O, now we take this infinitesimal element at an orientation, we should be able to find an orientation where there are only normal stresses like sigma 1 and sigma 2, but on these planes there are no shear stresses. Then these planes are called the principal planes, and the corresponding normal stresses are called sigma 1 and sigma 2. We call them as principal stresses. Okay, the reason why we are looking at these principal stresses is usually for isotropic materials we define failure based on the principal stresses. So let's see how we define it. There we use the failure theories. You might be knowing some of the commonly used failure theories like maximum stress failure theory. And then, of course, there is maximum strain failure theory, but we are also interested in the maximum shear stress theory. And then there is very commonly used the maximum distortion energy theory or the von Mises failure criteria. In all these failure theories, essentially what are we looking at? We try to look at the failure surface or the failure envelope. So let me draw it and show you, and then we can come back to what we mean by failure envelope. So these are usually plotted with respect to sigma 1 and sigma 2, which are the principal stresses. And if we are looking at the maximum stress failure criteria, it will be symmetric about both sigma 1 and sigma 2 because the strengths are the same in both the direction, in tension and compression. Okay. So this we are calling it as the maximum stress failure criteria, and these lines what we are now drawing are the failure surface. What does it indicate? If the loading is within the square, then the loadings are safe. But if the loadings are either on the square or outside the square, then the failure is occurring. So let's see for maximum shear stress, how does it change? So maximum shear stress, it changes in the second and the fourth quadrant, but in the first and the third quadrant, it overlaps with the maximum stress theory, normal stress. So this we are calling it as the maximum shear stress theory. And the blue one, we already showed that it is the maximum normal stress theory. And lastly, for the distortion energy theory, we know it's an ellipse. So let's show it with, okay. Okay. So the reason why we are again going through this is to highlight that we are looking at the failure surfaces to look at whether a particular component fails or not when biaxial strengths are applied, since we are now only looking at 2D stress state. Okay. With this background, now let's see how we look at the biaxial strengths for an orthotropic material, or for in our case it is the composite. So when we discuss about orthotropic material, the first thing we need to realize is it is very difficult to apply a failure theory, because what do we mean by a theory? A theory is based on some physical observations, let's say, which is related to the failure mechanism. So whenever we discussed about distortion energy theory or shear stress, we are very clear about how the failure happens in the material. But in composites, it's very hard to do that in that fashion, because the failure can happen in multiple fashions. We have seen it in two slides earlier, saying that it can happen through fiber fracture, fiber buckling, or matrix failure, or we can also have a failure between the matrix and the fiber. So which means when we come to the composites, starting from the failure mechanism to come up with a failure theory is very difficult. So instead we focus on failure criterion. which where we are mentioning that these are based not on failure mechanism. Or we should also call this as phenomenological models, meaning that we are based uh, developing these failure criteria based on experience, meaning the more we test, we get a sense of how things fail, and based on that, we are coming up with these failure criteria. So essentially, these are less analytical and more empirical. But the approach we'll follow is semi-empirical, meaning like we are not just blindly going with the experiments, because then we need to do lots and lots of experiments for us to come up with these to decide whether something fails or is it safe. But we'll follow a semi empirical formulation where we can use both an empirical relation as well as analytical relations to decide whether something fails or if it is safe. So here we said for orthotropic materials, we are going with the failure criteria instead of the failure theory, which we used in the isotropic materials. But let's also see what are the other differences with isotropic materials. So one major difference one should appreciate is when we talk about strengths in an orthotropic material, we should see that these strengths are different in different directions, meaning whether you are applying in tension or compression, the strengths are not the same. Unlike in isotropic materials, where most often we assume that the strength in tension and compression are the same, which means the strengths are different in tension and compression. And why do they do so? Because we know that the failure mechanism is different. Let's say in tension, it is fiber fracture, whereas in compression, it is fiber buckling. So we don't expect to have the same values of the strength in both tension and compression. But they're also different whether you are applying the loads along the fibers or perpendicular to the fibers. So again, we know that these strengths are very high when you are loading along the fibers, but transfers to the fibers or perpendicular to the fibers, the strengths are less. So what it means is, current previously we have been following these principal stresses, meaning no matter what is the multi-axial load given, we try to find out what are the sigma 1 and sigma 2, which are the stresses or the planes where there are no shear. Once you know what is sigma 1 and sigma 2, then you compare those with some criteria. But here we cannot do that because let's say the maximum stress is there on sigma 1, which is the principal stress, but then even the strengths along that direction are high. So meaning that though the stresses are high along the direction 1, it might fail maybe in direction 2 where the strengths are low. So we cannot blindly use even these principal stresses sigma 1 and sigma 2. Instead, what we do is we use the stresses along the fibers and perpendicular to the fibers. Unlike isotropic materials where we used principal stresses to come up with a failure criteria, here we use the stresses in material coordinate system. So meaning when we talk about stresses sigma 1 and sigma 2, we mean stresses along the fiber and stresses perpendicular to the fiber. So now let's see why we are changing the approach. Earlier, we are talking about principal stresses, meaning those planes where there are no shears for isotropic materials. But now, instead of using the principal stresses, we are talking about stresses in the principal material directions. What do we mean by principal material directions? These are along the fibers and perpendicular to the fibers. That's why we said sigma 1 is stress along the fiber and sigma 2 is stress perpendicular to the fiber. Let me show this with an example. Let's say we take a composite lamina, and let's say these fibers are oriented at an angle such that along the fibers we defined it as direction 1, and perpendicular to the fibers we are defining as direction 2. And let's say here the loading is uniaxial along the body coordinates. So let's say this is sigma x. Now let's see how we do the stress transformation, where we go from the body coordinate stresses to find what are the stresses in the material coordinates. So here the only stress applied is sigma x, and all other stresses are sigma x is the non-zero value, and the other stresses like sigma y and tau xy are 0. So now let's see, for this loading case, how do we find the stresses in the material coordinates? For this, we use the stress transformation, which we already discussed few videos back, where we use this transformation matrix T. So in this, we said sigma y goes to 0 and tau xy goes to 0. So now I should be able to write what are sigma 1. Sigma 1 is cos square times sigma x, and sigma 2 is sigma x times sine square theta, and tau xy, okay, it should be tau 1 2 is sigma x sine theta cos theta with a minus sign. Okay, so these are the transform stresses which we need to use to compare with the failure strengths. So in summary, there are two important points when we discuss about orthotropic materials. First, here we'll be focusing on failure criteria instead of the failure theories. And the reason is because it is hard to focus on the failure mechanisms because there are several failure mechanisms which compete with each other. And trying to come up with an analytical formulation is tedious, and it is a point of scientific research. And the other major difference is, here we are looking at the principal stress directions, meaning that sigma 1 and sigma 2, here we are referring to stresses along the fibers and perpendicular to the fibers. Whereas for the isotropic materials, there the sigma 1 and sigma 2 are principal stresses. Principal stresses are stresses where the planes with zero shear stress. So this is how we differentiate between the orthotropic material failure and the biaxial strength failure. Now let's discuss about the few failure theories. We previously mentioned that the maximum stress failure criteria and the maximum strain failure criteria are ones we'll start with, because these are simple to understand and to implement. But after this, we will also discuss about Sahil and Hoffman, which are more practical and which are more commonly used. So let's start with the first one, which is the maximum stress criteria. So the maximum stress failure criteria is something which we are familiar with because it is similar to the maximum normal stress theory for metals. Okay. So essentially what we are doing is we say whether a material is safe or failing just by comparing with the failure strengths. So what are the failure strengths we are looking at? We say it is safe when the sigma 1 is less than the failure strength in, let's say, first start with tension, which is xt. But let's say if the loading is compression, then we should say that the sigma 1 should be greater than xc. Similarly, looking at the transverse direction, then we focus on the stress sigma 2 and say if it is safe if the value is less than yt, and if it is greater than yc in compression. But when it comes to shear, we only need to focus on S. So the stresses are tau 1 2, whether it is positive or negative, it should be less than the value or the failure strength in shear, which is S. So as we can see, we have 5 failure criteria to check whether a material fails or not. So here we can say that failure occurs when the stresses in material directions exceed the corresponding failure strength. Hmm. Now let's see for an uniaxial load how can we apply this theory. So let's again consider this lamina, and let's say it's loaded along the x-axis. So we are applying sigma x, and let's also show the fibers. So the directions 1 and 2 are along the fibers and perpendicular to the fibers. Okay. And these make an angle of theta. From stress transformations, we know sigma 1 is equal to sigma x cos square theta, sigma 2 is sigma x sine square theta, and tau 1 2 is minus sigma x sine theta cos theta. So now let's apply this to the failure criteria. So sigma 1 will replace it with xt at the limiting conditions where the failure occurs. So now I can rewrite this first equation as sigma x should be less than xt by cos square theta if it is in tension. But if it is in compression, we should say that sigma x should be greater than xc by cos square theta. Similarly, for the second equation, we can write this as sigma x should be less than yt by sine square theta, because again we are uh, looking at the limiting conditions where it fails. There we replace sigma 2 with yt. And for stresses in compression, we say sigma x should be greater than yc by sine square theta. And lastly, this can be shown as sigma x should be less than s by sine theta cos theta. So here we'll only look at the mod value, and we can then ignore the negative sign. Okay. But we should be able to combine these two equations into one and say that sigma x should be less than xt cos square theta, and it should be greater than xc by cos square theta. Similarly, I can combine these two equations into one to say that yc by sine square theta should be less than sigma x should be less than yt by sine square theta. And the last one, there is no change. So at the end, what we have is this, uh, though I would say these are 5 equations, so we have showed them in 3 expressions, let's say. So this should take care of stresses along the direction of the fibers, where we are looking at both for tension and compression. And this should take care of strengths perpendicular to the fiber both in tension and compression, and lastly the shear strength S. So if we apply these three expressions or the five failure criteria, then we can say whether a material fails or not. Even if one of these five failure criteria fail, then the composite fails. So again we are looking at the same example where we are loading along the x direction, and then we have fibers at an angle theta. So let me plot as a as we vary the angle theta, theta is equal to 0 to 90, in between let's say somewhere it is 45, and the y-axis let's say is sigma x. So in this particular loading scenario, what do we expect along the fibers? Along the fibers, are they in tension or compression? So it's in tension along the fibers. If it is in tension along the fibers, what is the failure expression we apply? We say we apply this sigma x should be less than xt by cos square theta. So now let's see how we can plot this. Since we know this cos square theta is less than 1, so it's an increasing curve. So let's plot this and show that from here it starts increasing. So this is related to, let's say, is xt. But we should also look at stresses perpendicular to the fiber. So perpendicular to the fiber, again we see in this uniaxial load sigma x, the nature of loads we get is perpendicular to the fiber, it's again in tension. Tension perpendicular to the fiber. So there we look at sigma x should be less than yt by cos square theta or sin square theta. Sin square theta. And lastly, for shear, it will be sigma x should be less than s by sin theta cos theta. I don't need to look at the other two criteria such as in compression, because for this uniaxial loading there are no compression along the fibers, neither there is compression perpendicular to the fibers. But now we have already looked at this equation, first equation. Let's see the second and the third equation. The second equation is yt. Usually the strength perpendicular to the fibers is much less than strength along the fibers. So let's say this is somewhere at xt, and here we are starting at yt. And since we are looking at sin squared theta at the denominator, it's again a increasing function. But this third expression s by sin theta cos theta, this varies with theta and it has an expression something like this. So meaning this we said is corresponding to yt, and this curve corresponds to the shear strength S. So if we have a condition like this, how do we decide failure? This failure is based on the minimum strength. So if we are looking at angles close to 0, we need to look at this part of the curve. But beyond this angle, we then focus on failure coming from the shear strength. And lastly, beyond this angle, we see the failure occurs because of the transverse strength in compression, in tension, white. So this should be the failure curve. Hmm. So essentially, there are few points to note about the maximum stress failure criteria. One, we note that there are cusps. What are these curves? These are these discontinuities happening at the intersection between these two curves. which are unrealistic, because if we look at the failure data of the same material from experiments, if I plot on the same plot, there I don't see a cusp, but from the theory what we are seeing here, we do see cusps. So we see cusps which do not occur in experiments. And when people have compared this maximum stress failure criteria with the actual experiments like epoxy composites, people noticed that the matching is not so good. Though it is reasonably well, it's not as good as the other failure criteria. So it does not match well with experiments. Okay. Though it didn't match well with the experiment, we have looked at it mostly for academic purposes, because we want to see whether whether we can apply this maximum stress failure criteria. And for some materials, it is reasonably okay. So people do use it in very rare occasions. Now let's move into the another failure criteria, which we call it as the maximum strain failure criteria. So as you can see, it is very close to the maximum stress failure criteria. The only difference is, instead of stresses, now we are focusing on the strains. So it is similar to the maximum stress failure criterion. Instead, here we are looking at strains. So previously, if you recall, we did define the failure strains shown as these 5 values: x epsilon t, x epsilon c. These are the failure strains in tension and compression along the fibers, and perpendicular to the fibers we wrote it as y epsilon t and y epsilon c. These are the strains in the tension direction as well as the compression direction for the transverse direction loading. And finally, the shear strain at which it fails. So here, how do we define failure? We say something is safe if the corresponding strain, here it is epsilon 1, which we will now find out what is the strain along the fibers. If this is less than the critical value, which is x epsilon t, then we say it is safe. But this strain can also be because of compression. So another expression we need to write is epsilon 1 should be greater than x epsilon c. So now we have taken care of both tension and compression. Similarly, perpendicular to the fibers, epsilon 2 should be less than the corresponding failure strain. And we also look at strain per in the compression loading. And finally, the shear strain, gamma 1 should be less than the corresponding failure strain as epsilon. Okay. So we are saying that this composite material is safe if all these 5 criteria are met. What are these 5 criteria? We are just comparing the strains along the fiber, perpendicular to the fiber, and in the plane shear strain with the corresponding fundamental strengths. Now let's look at how do we apply this maximum strain failure criteria. First, we need to find out the strains. How do we find the strains? For this, we invoke the strain stress relations. So in the earlier videos, we showed for a specially orthotropic material the relation between the strain and the stress given by this compliance matrix. So if we now look at these expressions, how do we find epsilon 1? So using this strain stress relation, we can now write epsilon 1 is simply 1 by E1 times sigma 1 minus nu 1 2 times sigma 2. Similarly, how can we write epsilon 2? That should be 1 by E2 times sigma 2 minus nu 21 times sigma 1. And gamma 12 is given as tau 12 by G 12. So this gives the three expressions we need to find the strains in terms of the stresses in the material coordinate system. But now let's see if we are applying uniaxial stresses as we discussed earlier. So now when I consider this uniaxial stress problem with sigma x applied in the x direction, and then we look at the fibers at an angle where these are the directions 1 and 2. So earlier we have shown the transformation of stresses where we showed sigma 1 is sigma x cos square theta, sigma 2 is sigma x sine square theta, and tau 12 is minus sigma x sine theta cos theta. Now if I replace these sigma 1s from, let's say, these equations 1, 2 and 3, in equations 1, 2 and 3, replace sigma 1, sigma 2 and tau 12 with sigma x and theta. Then we should be able to write it as epsilon 1 equals 1 by E1 cos square theta minus nu 12 sine square theta times sigma x. Similarly, epsilon 2 can be written as 1 by E2 times sine square theta minus nu 21 into cos square theta times sigma x. And similarly, gamma 12 can be written as minus 1 by G12 times sine theta cos theta and sigma x. Okay, so what we have done till now is only to show the strains in terms of sigma x, which is the applied load, and sigma 2 in terms of the applied load sigma x, and lastly again gamma 12 in terms of sigma x and the orientation angle theta. So in the next slide we will rewrite this expression where we bring the sigma x to the left hand side and then rewrite these three equations. So these are the three expressions now written where sigma x is moved to the left hand side. In the limiting case, I can replace epsilon 1 with epsilon x t. But mind you, how can we write this strain? We previously said this strain is written in terms of the strength xt by E1. Similarly, in compression, the failure strain is xc by E1. Now moving to the transverse direction failure strains, yt by E2, and in compression failure strain is yc by E2. And lastly, okay. So what we'll do is now we'll replace in the limiting case, we'll replace the strains in these expressions. Now let's call this as expressions 4, 5 and 6. In equations 4, 5, 6, we'll replace the strains with the failure strains. And this failure strength can again be written in terms of failure strength is what we have shown here. So we'll write this as sigma x is equal to, first we'll replace epsilon 1 with the failure strength x of et, but once we multiply that with e1 we get it as simply xt. So it is simply xt by cos square minus nu 1 to sin square theta. So in the limiting condition I should not write it as equal to, but simply I should write it as less than. So we are saying the composite is safe when the sigma x or the applied load is less than this expression. Similarly, for compression, we can write it as sigma x should be greater than xc by cos square theta minus nu 1 to sin square theta. And when we look into the transverse direction, should be yt by sin square theta minus nu 2 1 cos square theta. And looking for compression, it should be greater than yc by s square minus nu 2 1 cos square theta. Okay. And lastly, for the shear, we can write it as sigma x should be greater than s by g1, s by sin theta cos theta. So like in the maximum stress failure criteria, these two expressions can be combined and written in one expression as, we can bring this sigma x to the middle and then write it as xt by cos square theta minus nu 1 to sin square theta and xc by the same cos square theta minus nu 1 to sin square theta. Similarly, for the other two expressions in the transverse direction, now I should be able to write it as yc by sin square theta minus nu 2 1 cos square theta should be less than sigma x should be less than yt by sin square theta minus nu 2 1 cos square theta. Okay. So these are the final three expressions which we need to apply for the maximum strain failure criteria. And mind you, here we are only looking for the when it is uniaxially loaded, sigma x is the only non-zero stress applied. Okay. Before we conclude, let's look at some salient points of the maximum strain failure criteria. The first major point is, if you look closely, we see we now look at the Poisson effect. So we write these expressions in terms of nu 1 2 and nu 2 1. So which means the Poisson ratio is in the expression. So why do we stress it? Because this is something which is absent when we are looking at the maximum stress failure criteria. But when we are discussing now about this maximum strain failure criteria, only then we look at this Poisson effect which are coming into the failure expressions. Coming to the second point, if we compare this failure criterion with the experimental data, we still find discrepancy. Meaning that similar to the maximum stress failure criterion, even with this maximum strain failure criteria, still we haven't reached to a failure criteria which is good and which can be applied to most of the composites. That is a strong motivation why we have to discuss about the other two failure criteria, which we'll be discussing in the next video. So in summary, what we have discussed in this video is we first reviewed the five fundamental strengths in the lamina, and then we moved into this biaxial failure criteria, where we said, okay, we need a failure criteria which can be applied to know whether something fails or if it is safe when applied with multi-axial loads. So we started with the isotropic materials to give some review of what we meant by failure surface or the failure envelope. So in the isotropic materials, we were using the principal stresses to come up with this failure surface or the envelope. But when we discuss about the orthotropic materials, we made few changes. One, we said we cannot go with the failure theories. The reason is failure theories are based on failure mechanisms. So trying to come up with analytical expression based on the failure mechanism. But in composite, since there are several failure mechanisms which are competing with each other, coming up with a theory which takes care or the derivations are based on these failure mechanisms are difficult. Mostly because there are several failure mechanisms involved and things get complicated because of the complex stress strain relations. So instead what we are doing is we are focusing more on the failure criteria. And secondly, we also made one major change. Instead of working with the principal stresses sigma 1, sigma 2, now we are looking at stresses along the principal material direction, means stresses along the fibers and perpendicular to the fibers. So mind you, here the coordinate system 1, 2 is the material coordinate system, where 1 is the direction of fiber and 2 is perpendicular to fiber. So having said this, then we started looking at two of the failure criterions, essentially the maximum stress failure criterion and the maximum strain failure criterion. In both these failure criterions, we noticed that uh, both are still not matching with the experiments, which means there are discrepancies, and that is a strong motivation, we said, why we have to learn few other failure criteria before we say we have something to apply and predict the failure. So that we will be discussing in the coming video. Thanks for it.